since it is a very advantage that you have the advantage of replaying the recorded videos, and which also downloadable. Okay, so if you have any doubt, you download it and revisit the video again and again. So I think any sort of problem, at least in my portion, will be solved. Okay, and after that, if you have any problem, you can come to college. If you just inform me, obviously. Uh, I will conduct doubt clearing classes for about a group of students. Only one, two will not be sufficient. At least 10, 15 students. If you have any doubt, you can come. But that is maybe after because from 15 to 17 we will be busy actually with the conference, and from 20 to 20 then from that 3 days, 20 to 22, 20, 21, 22 we will have internals, and from 25th we will have our winter vacation. So if you have any doubt, you can just inform the faculty and you can come to college. Obviously in a group. Okay, no faculty will want to teach one student or two students. Obviously in a group, if it is there, it will be good. So, so last day we learned how to develop the flexibility matrix. Okay, and today we will solve numericals based on flexibility matrix. Okay, so last day, as I told you, I was not able to complete the presentation. So this presentation I will send you. Last day I discussed regarding the spring deformation, all these things. That is from the force displacement relationship. This concept of stiffness and flexibility method has been derived. Okay. So from the force displacement relationship, we can see from here this uh, from the force. So the flexibility is also known as force method, and the displacement method is also known as stiffness method. Okay, and we learned all these things I taught you last day. The same thing which I taught you, I made you write in the board. I have typed in the PPT. Okay, all these things, all the methods which are falls under force and flexibility method. So now coming to, I taught you how to develop a matrix. I taught you we solved this numerical. Okay, if you want, you can solve this numerical also. How to develop flexibility matrix. AB is a simply supported beam, and you have the end moments. Okay, moments are there only, and we have three coordinates: 1, 2, and 3. So if a simply supported beam is there and a point load is acting at C midpoint, and if there are moments at the support, then what will be the flexibility matrix? So as you know, I have mailed you a chart. I have mailed you a chart of the slope deflection results for various types of beams. I have mailed you beams like single supported beam under UDL, single supported beam under point load, then cantilever beam, all these, then beams under moments. So that chart is very important for your MCQ as well as for your matrix analysis numericals. Okay. Similar chart I will send you for stiffness method also. Okay. So coming to now the procedure to analyze problems using matrix method. So last day what we had learned that how to develop the matrix. So if we see there, for example, if we have 2 by 2 matrix, then it will be for the two, that is 4 elements or 4 flexibility coefficients. If we have 3 by 3 matrix, then we have none elements like this. Okay. So this is, as I told you, if we have 2 coordinates, then it will be 2 by 2. If it is 3 coordinate, 3 by 3. Another important property which I missed out last day, that is the, see here, the 2 properties which are very important for MCQs also. Simple property, the flexibility matrix will be a square matrix. I discussed it last day, in which the diagonal elements will be non-negative and non-zero. That means it will not be negative, and as well as the diagonal elements are non-zero. It is observed when we solve it for flexibility as well as stiffness matrix. Okay, very important property. Another is that I discussed last day, that the order of flexibility matrix will be equal to the degree of static indeterminacy. That is, if we have number of redundants 2, number of unknowns 2, then it will be 2 by 2. If we have number of unknowns 5, then it will be 5 by 5 matrix like this. Okay. So now, so if 1 1, if 1 2, what are the coefficients stands for? I discussed here. So I told you we will go first column wise. So whenever we solve the matrix, whenever we develop the matrix, we will do it column wise. So if you see here, if11 is the displacement at coordinate 1 due to unit force at coordinate 1. Then F21, the first two elements of column, if you see the first two elements of the first column, then we will go for second column. Okay. So F21 displacement in direction 2 when unit force applied at direction 1. So today we will solve the problem. Okay. So we will solve a big numerical. We will solve continuous beams. So to develop flexibility matrix is a small part. We will apply that flexibility matrix into some compatible equations and we will solve it. Okay, that is the main important thing. Before coming to that part, let us see. So what is the basic requirements? Okay, what is the basic requirement? I will come to the whiteboard. But before that, what are the basic requirements to find? See, so procedure to analyze, that is the now we will go for numerical problems using flexibility matrix. Okay. So it is very important that, see, the first point is very important that the structures should be statically determinate and stable structure, which is often observed if the structure is not uh, determinate. If it is indeterminate, that we have to convert it into determinate structure. See, very important. It is statically determinate and stable structure, which is obtained by using a sufficient number of internal or external reactions. That means it might happen obviously like this continuous beam ABCD, this beam. It is an indeterminate structure. If we apply determinacy ds, degree of static indeterminacy ds equals to Re minus 3. That is number of unknowns, total unknowns minus 3. That is, here we have the external redundancy Re 5. So here we have, if you see here, it is pinned. Here we have two unknowns, one unknown, one unknown, one unknown. Okay. So 2 plus 1 plus 1 plus 1, 5. So number of total unknowns in the beam is 5. Number of static equation we have 3. So 5 minus 3, we have 2 unknowns. Okay. So which are the 2 unknowns? So basically, so this is an unknown. So now we have to find out that we have to convert this indeterminate structure. So it has this beam or the structure contains indeterminacy or redundancy. So we have to convert this into determinate structure and then we will solve it. Okay. So unknowns here, we know the moment at A is 0 and moment D is 0. So basically we know that moment A and moment D are 0. So which is unknown? Unknown is slope at B and the moment B and A, B and C. So moment B and moment C, they are unknown. Okay. The two redundancies. So we have to identify this thing. So now coming to the various cases which can come in flexibility matrix method, numericals. Okay. There can be various cases. So particularly, I will tell you in the whiteboard that to solve any numerical using flexibility matrix method, there are two ways. One is either we can consider the forces, that is, or the reactions. For example, I have supports here. If I see here, for example, so there are two types of ways by which we can solve any continuous beam using flexibility method. First is, what we will do, wherever there is unknown, we will remove the supports. See, at B and C, we have removed the supports. So we have introduced a reaction, obviously. So there are two ways by which we can solve, either taking the redundants as reactions or forces, or sometimes taking the unknowns as moment. Okay. So we can, so there are obviously there are unknowns. One unknown is there is reaction at B. The reaction at B which is unknown or redundant at B, R, C. Okay. These are unknown. As well as we have moments at B and C. There is another, the second method by which we can solve flexibility matrix method. So there are two main ways. One is we can consider the reactions or forces as unknowns or redundants, the amount which is to be found out, and moments at the supports, that also we can take as unknown. The moments we take as unknown in the slope deflection method and moment distribution method we have learned. So we usually find out what? We usually find out the slope, the reactions, and the bending moment, right? The end moments using slope deflection. That we have learned. This way, this method we have learned. Another method is that we can consider the reactions as unknown. Okay. We can consider the reaction if we remove the supports, or if we keep the support, obviously there is a reaction that is unknown. So there are various cases by which we can approach, or we can approach the flexibility matrix method. See, I told you that whenever we will approach flexibility matrix method, there are various methods. Either we can use moment area method, or we can use conjugate beam method to solve the to find out the flexibility matrix, right? So first, see here, case one. So case one, what is? So consider external reactions at B and C as redundant. See here, what I did, I removed the supports at B and C. Here, see, I've removed the supports at B and C. Okay, and so I have taken the supports at B and C as unknown, redundant. So the release structure, so this is called release structure. It is called primary structure or release structure. Okay. So I have converted this indeterminate structure into determinate, because it is single supported beam now. AD, only two supports. So this release or primary structure can be obtained by removing restraint offered by reaction. That is case one. That is, I am removing the supports where unknowns are there, and I am showing the reactions at B and C. So I have shown two coordinates, coordinate 1, and coordinate 2. Case 1. Second case, if bending moment C, case 2, if bending moment at B and external support at C is released, that means I have one bending moment at B which is unknown, as well as support reaction at C is unknown. Okay. So see here, A, B, C, and D. Okay. So what I did, so the same beam, see here how I am analyzing. I have removed the support at C and I've kept the support at B. And I am finding out the moments at B and moment. So coordinate at B is 1, that is the bending moment, and coordinate at C is 2. So at C it is unknown reaction, while at B it is moment. So here I am dividing into two different bodies. I am dividing into two different bodies. One is AB beam, simply supported beam, where we have unknown moment B. Another, this one body, body 1, it is simply supported beam, determinate structure. Another is body BD, it is a simply supported beam, where we have unknown at B as well as coordinate at C. What happens, this case 2 is a combination of two cases. That is, here I am considering the moment as redundant as well as the reaction as redundant or unknown. So these two, basically we do not use this method. We basically follow this case 1, or we can follow case 3. Case 1, what we, it is very simple actually. It is simple to analyze. It is simple to solve. Practically, I am saying it is simple to solve. So case 1, what I am solving, I will use conjugate beam method or moment area method, where reactions are unknown. Similarly, in case 3, I have not discussed case 3. Case 3 is what? Only the bending moments are taken as redundant. That is, see here, bending moment at B and C is released. Then the release structure comprises of three simply supported beams, A, B, B, C, and C, D. So see here. So I am taking only the moments. So we will solve these type of numericals only using two methods. Either using flexibility method, that is the taking the reactions as unknown, one method, and the alternate method is taking bending moment as unknown. You see here, moment B and moment C is unknown. So we have divided into three different beams: AB, BC, and CD. AB, BC, and CD. Okay. So in this manner, we can do this. So practically, why people are leaving and joining, I don't know. Practically, we will follow case one. Either we will follow case one and solve. Then what we will find out? We will find out the reactions at C, B and C. So this is which is unknown at B as well as C, which is unknown. This we can find out using case one. And if we find out the bending moment, then we have to follow case three. Okay. So this is the thing. So now the very important thing is that, for example, we are coming to the numerical. That is, we have AB cantilever beam, coordinate 1 and coordinate 2. Coordinate 1 in the horizontal direction and coordinate 2 is vertical direction. So we will find out, see here, in flexibility method, the unknown forces are taken as redundant, and we will have 2 by 2 n by n matrix. So basically, so we will find out what is the unknown. The unknown is the displacement, as I told you. In flexibility method, what is flexibility? The displacement corresponding to the unit force. Okay. So here, the total displacement. See, we have two coordinates. I am taking an example. Okay. I am taking an example. Okay. So we have two coordinates, 1 and 2. So we have deflection at 1 and 2 is how much? Flexibility matrix into P1, P2. P1, P2 are the forces which are given. There is a external forces. Okay. So if you so with this, so we have equation actually. We have derived this matrix form by equation. So what will be the equation? Delta 1 will be F11 P1 plus F12 P2. Similarly, delta 2 will be F21 P1 plus F22 P2. Let me write in the whiteboard. Okay. Let me write in the whiteboard. Okay. So what I am sharing, let me share the screen again. Yes. So these, so if you pin the other window, you can see that practically what is the final element or the final equation. Basically, now we are going to derive the, or we are going to uh, develop an equation. It is called compatible equation. Okay. In flexibility matrix, it is also known as compatibility method, as I told you. So flexibility, it is known as compatible equation, while in stiffness, since it is equilibrium method, it is known as equilibrium equation. So now we are confined to flexibility method only. So it is known as compatible equation. So what is the thing? If you see, if you see in the window here, for example, I have shown a cantilever. There are two coordinates, 1 and 2. So what is my definition of flexibility? Okay. So this is the thing. Okay. So so now I'm stopping the sharing. Okay. So now, what is my flexibility? What is the basic Definition of flexibility, if you remember, that is how much displacement, how much displacement for how much displacement is occurring for unit force, right? How much displacement for unit force, unit force where at respective coordinates, right? At respective coordinates. So basically, my compatible equation, see it is compatibility equation is how much? That is the unknown. So the unknown displacement. So here I have represented two coordinates. So I will represent two only, delta 1, delta 2. Okay, delta 1, delta 2. Now this delta 1, delta 2 will be how much? As I told you, that is flexibility matrix which we have got due to unit force and multiplied with P1, that is the unknown load, that is P1, P2 is the external loads. So therefore, what we can write? So basically, the equation was derived like this. Can find equation, that is the total displacement. See here, delta 1. Total displacement at coordinate 1 will be F11 P1 plus F21 P2. If you do the matrix multiplication, this will be equation 1. Understood? This will be equation 1. And another is there, that is delta 2. Do the matrix multiplication. That is delta 2 will be F21 P1 plus F22 P2. Is the board visible?
Yes, sir.
Okay. So this is from, basically this is the main fundamental. That is, we are going to find out the displacement. Displacement, it can be in terms of deflection or it can in terms of slope. Okay. Right. So delta 1, delta 2, this equation we can find out. So we can write from here what will be the compatible equation, that is delta equals to F matrix into P matrix. So now the P matrix will be how much? P matrix will be F inverse into delta. F inverse into delta. Okay.
Sir, nothing, sir.
Yes. So F inverse is because matrix, it will be inverse. Okay. So this is basically known as, since flexibility method is known as compatible method, so it is known as compatibility equation. Compatibility equation. Okay. Now this delta 1, again if you be, I will come to that point where I will show you the stepwise. This delta 1 is basically equals to, delta 1 is what? That is the total, that is total, what I told you, total displacement. Total displacement at coordinate 1, that will be how much? If you be, when we will do the problem, you will understand. Delta 1L. Delta 1L will be the deflection due to external loading. L will be external load. Displacement at coordinate 1 due to external loading plus displacement at coordinate 1 due to redundant, which is unknown. Okay. Similarly, total displacement at 2 will be, will be the displacement due to this L means external loading. That is that means it can be point load, it can be UDL given in the question, and delta 2R. This means under redundant load. Okay. So delta 1R and delta. These are called due to redundancy is unknown, and these are due to the external loading. Okay. So to find all these things, we will apply, either you can apply moment area, you will get the same answer, moment area, or conjugate beam, method. Okay, you can apply anything, no problem. Okay, so now we will come to the stepwise method. Okay, stepwise method we will come. So again, I'm starting sharing the screen. Okay, so now I'm sharing the screen. So now we will, if let me show you, that is, we will now come to step 5. Okay, so for I told you that we will solve, we will solve for a continuous beam, a full-fledged beam, which we have studied while studying any method, slope deflection, moment distribution, any method. So first step, see here. So what is first step? First step is to find the first is the find the degree of static indeterminacy, that is ds. Okay, the straightforward we will find out the degree of static indeterminacy ds. Now identify the redundancy in P in such a way that the release structure remains stable and determinate. That means we have to find out the ds, and as well as we have to find out which are the unknown. Where are the unknown? So let me take here. If you see, if we find out the ds here, 6, 10, 3 plus 1 plus 1, that is 5 minus 3, 2 unknowns. That is the ds value is 2. If you do the find out the degree of static indeterminacy, ts, that is what RE minus 3, that is 5 is the total number of unknowns, minus T number of static equation, that is 2. Okay, so here we have 2 unknowns at A as well as B. Okay, and P1, P2, see here, P1, P2 are the external loads which is given in the question. Okay, AB is length L1, BC is length L2. So we will take, so reaction at A will be unknown, first unknown R1, and reaction at B R2. Okay, so here I am taking the reactions as unknown, very important. Okay, so now, so first step is very simple, find out the degree of static indeterminacy and identify where the unknowns are present. Second, now what is the step 2? We will remove the redundant. See, remove the redundant, that means we have, see, at A and B we have removed the supports and assign one coordinate direction of each redundant. So I have removed the support at A. So this is A. And so instead of removing the supports, what I have introduced? An unknown reaction. Similarly at B, I have removed the supports and this is an unknown reaction. Coming to step 3. So based on this part, that is I have removed it. Okay. So one coordinate, two coordinate. So by removing this, what will be I will get? I will get the coordinates F. So at 1 it will be F11, F21, and at 2 F2, F12, F22. So now we will step 3. We will develop the flexibility matrix. So develop the flexibility matrix for above coordinate systems and find out the inverse of flexibility matrix, F inverse. Okay, because inverse is required because we will require in the last, that is compatible equation. Coming to step 4. So in step 4, we will remove the redundant and obtain basic release structure with given loading. Now see here, till now what we did, we had removed the supports as well as P1, P2 is see here, P1, P2 have been removed. P1, P2 have been removed. In this case, the force was unit, the unit force, as I told you, to obtain flexibility matrix, we will keep the force as unity. Okay. So now in the step 4, we will insert the P1 and P2 where we had removed. The points where P1, P2 was there, we will remove those. Okay. It can be UDL. Here I have represented point source. It can be UDL, it can be UVL, any loading. Okay. So now we will put P1 and P2. Okay. In step 5, we will find for the basic. So it is called release structure. So it is called released or primary structure. Okay, as I told you, it is called whenever you are removing the supports, that structure is basically known as release structure or primary structure. Okay, so step 4 for basic release structure, find the deflection due to given loading. So now, due to this P1 and P2, we will find out what delta 1L, as I told you, delta 1L and delta 2L. So delta 1L and delta 2L will find out deflection due to P1 and P2. Okay. So finally, the last step will remove the loading and apply redundant forces. So this will be my final equation. So the redundant, so delta 1R, that is a deflection due to redundant, is how much? F11R1 plus F12R2. See here, F11 flexibility coordinate plus redundant reaction R1. F12 redundant reaction R2. That means at coordinate 1, I am finding out the deflection due to redundant force, that is R1 R2. Similarly, at coordinate 2, that is the deflection due to redundant force at coordinate 2 due to R1 R2. And so now I have inserted this in the matrix form. Okay. Finally, matrix form. So I got delta 1R, delta 2R from this. And here delta 1L, delta 2L. Now what will be my final delta? As I showed in the whiteboard, that is delta 1L plus delta L plus delta R. Okay. So this is how we will solve the question. So we will solve the question in two manner. One is either first method will be we will take the reactions unknown and we will solve the same question. Bending moment is unknown. Okay. So now we will solve a question. So I have not typed the question in the PPT till now. So I will write the question in the board. Okay. So in the examination also you will get two types of question. Either in flexibility as well as in stiffness, you will get two type of question. That is either you have to develop the flexibility matrix only, okay, or you have to solve a full-fledged problem using flexibility matrix method. That is flexibility. Again, for stiffness, you have to develop the stiffness matrix, or you have to solve the total continuous beam using stiffness method. Okay. So see here, today with the problem which you are going to solve is by two main methods. That is taking the unknowns as forces as well as unknown as moments. In Bhavigatti, if you find in the book, in Bhavigatti book, SS Bhavigatti, they have solved the problems taking moments as unknown. Okay, they have taken moments as unknown. So finally, if I tell you to draw the bending moment diagram, so please find the question. If I tell you that analyze the continuous beam using flexibility method and also draw the bending moment, then you have to take the bending moment or the moments at the support as unknown. Okay. So now we will solve the. So today we are doing flexibility method. The next class, as I told you, on Wednesday from 2 to 4 p.m. I'm reserving it. Please make sure if any faculty tells you to take he or she will take class in that slot, please inform that I have booked. Okay. So now, so for flexibility method, what I told you that we have to remember moment area method. Okay. First of all, we have to remember the chart. Have you got the chart which I sent you in the email, Google Classroom?
Yes, sir. Yes, sir.
Time to
স্যার ওটা
time,
তো
please
স্যার
do
ওটা
check the
স্লোপ ডিক্লেশন মেথডে ছিল তো চারটা।
ওটা slope deflection method na. The values which they have been got using slope deflection method, okay, the values we have got from slope deflection method, but those values are basically required in flexibility matrix method. Okay,
ওকে স্যার।
to develop the matrix, develop the flexibility matrix, we require that chart. Okay, done. So now we will solve the problem. So I told you we have to remember the moment area method, or you can remember conjugate beam method, any two methods, and that chart. Okay, see, numerical problem, numerical problem. So since it is difficult for you to find out the all the values, basically the values which are given in the chart, they have been obtained from there's a one chapter in strength of material book, that is slope deflection in strength of material. Structure analysis one. There's another chapter called slope deflection, that so using that method, and another chapter is there, it's called fixed beams. So from those chapters, the values have been enlisted in the chart. Okay. So if I didn't give you the chart, it will be difficult for you to remember all the values for different beam coordination. Okay. So numerical problem. So we have to solve, complete, solve, or analyze continuous beam. Solve or analyze continuous beam using flexibility matrix method. Using flexibility matrix method. Okay. So we will, for example, let me take a numerical. So we have taken a prop cantilever beam of two, considering two span. ABC. So ABC is the continuous beam, prompt cantilever beam. EB is under 60, so we have to solve. Okay. So as I told you, flexibility method, there are two unknowns. Reaction as unknown, you can write down reaction as unknown. Either reaction is unknown or moments. Moments as unknown. So flexibility method we can solve using two ways. Either reaction is unknown or moments is unknown. Okay. In SS Bhavigatti, they have taken this method. In SS Bhavigatti book, they have not taken this method. Not a single the numerical. Okay. In other books, in CS Reddy, in Gupta and Gupta, they have taken this method also. Okay. But if I tell you to find out the bending moment, you will use this method. If I tell you to find out the shear force diagram, you will use this method. Okay. So ABC AB is. I hope all of you know the syllabus of first internal. The syllabus of first internal is, for my portion, unsymmetrical bending of beams and curved bars. Okay, unsymmetrical bending of beams and curved bars, hooks, not beams. Okay, curved bars is a hook which we have done, crane hook, all these things. AB is 60 kN per meter, and here we have taken point load BC 100 kN at midpoint. So AB, so let us draw the diagram. So AB is 4 meter and BC it is 3 meter, and the point load is acting at the midpoint. So A, B, and C. A, B, and C. Okay. And here EI is constant. So for AB, the pledged rigidity EI is constant same. Similarly for BC, EI is constant same. So AB and BC. So now we will go with stepwise. Step one. Step one. Step one is a what way to find out the DS static indeterminacy. Find out degree of static indeterminacy and identify the redundant. Redundant means unknown. That means जो हम लोग को निकालना है, जेटा से बात करते हैं, okay? जो हम लोग को निकालना है, that is basically known as unknown, or in a very good technical term, it is known as redundant. Redundant or okay. So here this is first of all method one. Please write down on the top this method one.
Sir, find out DSR for application.
Method one. DS and identify redundant unknown agent and identify redundant or unknown. Yes, sir. Simple. See here. We will find out DS first. So at fixed end A 3. So 3 1 1. So DS is RD minus 3 for beams. So RD is the total number of unknowns at A fixed end 3 plus B1 plus C1 minus, so number of unknowns is 2 here. So first we will be using method 1. So as per method 1, so we are taking, so assume reaction at B R1, a reaction at C R2. আমরা আমি unknownটাকে বার করলাম. First I have found out the unknown and I have identified where the unknowns are there. Now I will put the coordinate direction. I will put the coordinate numbers 1 and 2. That is very important. Okay, C as B is 2, C is 1. So add B, we are taking 2 and 7. So the chord. So I have identified 2 locations where unknowns are there at C and B. Okay, so coordinate 1, C as 1 and B as 2. Okay, so therefore we have assumed RB and RC is redundant. So therefore you can write down RB is equals to R2 and reaction at C is taken as R1. Are the two redundant reaction? Correct. Step 2. Step 2 is what? Step 2 is to develop primary structure. Develop release structure. Released or primary structure. Develop release of primary structure. That is how much? So now we will remove the support. So at B and as well at C, I have removed the support. This is the primary structure. So I removed the supports. Also, I have removed the external loading. Only I have shown that instead of removing the supports, I have shown an addition then and unknown coming at C, that is the upward reaction. While at B, again upward reaction because I have removed the support. If I am removing the support, obviously there will be I should put the reaction. If I do not put reaction, then it will be unstable and it is unrealistic beam. Okay. See. So now, based on this, what we will find out? We will find out what? We will find out the flexibility coefficient. So step 3 you can write down. Find out the flexibility coefficient. Flexibility coefficient. Okay. So what is what will be the flexibility matrix? We have two coordinates. The matrix will be 2 by 2. So the matrix will be 2 by 2. That is F11, F21, F12, F22. It will be 2 by 2 matrix. Okay. So therefore, first column to develop the flexibility matrix I taught you last day. So to find out the first column, put what? Put force equals to 1 kilonewton, where at coordinate 1. At coordinate 1, put F equals to 1 kilonewton meter. So 1 kilonewton because reaction. So here the unknown is reaction. F11. So if I put 1 kilonewton here, what will be my deflection? Obviously, there will be deflection PL cube by 3I. PL cube by 3I we know. That is the deflection. P is 1. So 1 into 3. So L is how much? So F11 is. So at C, we are putting 1 kilonewton. B and C. So at C, I am putting 1 kilonewton load. Okay. So due to this, I will find out F11, F21. F11 is that is 3 cube by TEI. So P is 1 kilonewton, PL cube by 3I deflection. So, it is so F11 no? So the length is total 4 plus 3 7. L is from this length, so A to C. So say 4 meter plus 3 meter, 7 meter. So PL cube by 3I, 1 into 7 cube by 3I. So this will be 340 by 3I. Understood why we require that chart? That chart is very important to find out the flexibility matrix. Okay. F11. Now F21, we will not make the trouble because F21 will be equal to F12. using the Maxwell's reciprocal theorem. So now case 2, that is case 1. In case 2, A, B, C. Now we will put reaction 1 kilonewton at B. We will put reaction 1 kilonewton at B. So here we will get F22, F12. So first case F11, F21. So F21 we are not finding out, directly we will find out from F12. So reciprocal theorem. Okay. Now coming to case 2. Case 2 means this beam. So therefore case 2. So F22 first. F22 will be what? PL cube by 3EI. Same way. P is 1 kilonewton. So 1 into 4 cube by 3EI. 4 cube by 3EI. It is coming 64 by 3EI. 64 by 3EI. Okay. So here I'm putting unit load at B, coordinate 1, coordinate 2. So now coming F12, that is the deflection at 1 due to unit load at 2. So this how we'll find out. See here. This will be delta 1. See here. This will be deflection at B. So coordinate 1 is B. So this we are writing deflection at B plus slope, deflection at B plus slope at B into length of B. Very interesting thing. F11 was deflection at coordinate 1 due to unit load at 1. F21 I have not find out because it is difficult to find. So I will wait for case 2. So in case 2 I put unit load at B, that is F22 will be what? Deflection at 2 due to unit load at 2. F12 will be what? Displacement at 1 due to unit load at 2. So I am putting the 1 kilonewton here. What will my deflection at this point? So this will be, so it is something like this. The diagram will be look like this. Okay. So this is delta B. And what this will be? So this will be delta B plus theta. So theta into L. That is why F12 is delta V plus theta into LBC. That means the delta B, the diffusion of delta B will be same like till this point, and extra it will be theta into L. If you take a triangle, if you consider that I'm not considering the curve, I'm taking triangle. So tan theta, from tan theta, theta very small, so tan theta almost equals theta. Theta almost equals theta. Okay. So from here I found out F12 is delta B plus theta B plus LBC. That is the slope at B plus length BC. So therefore delta B will be same. That is L cube, that is 4 cube by, so deflection at B will be what? PL cube by 3EI, that is P is 1, so L is 4 meters, so I'm measuring here. So 4 cube by 3EI plus slope at B. What will be slope? Slope is PL square by 2EI. PL square. P is 1. T square by 2 EI into length BC, that is T. So if
Sir,
12 is this, বলো
স্যার ডেল্টা বি কোন ভ্যালুটা একবার বলবেন?
ডেল্টা বি হচ্ছে এই ডিফ্লেকশন, এইটুকু ডিফ্লেকশনটা এটা এই যে এইটুকু ডেল্টা বি ইজ obviously present at C here, আরো এক্সট্রা হয়েছে, so delta b is deflection at B, okay, so this delta b will be same at here, but at C it is more deflection because it is at more length, so you know that more the length from the support, more will be the value of deflection. So this theta L is the extra part, so delta b plus theta L. So therefore F12 is coming as 136 by 3. 136 by 3. Okay, so we have got F11, F21, F21 will be same, 136 by 3 EI, F21. Okay, so now we will put this step 4 will be, so all of you write this down.
স্যার
বলো
স্যার বলছি এখানে ডেল্টা বি এর যে ভ্যালুটা এসছে 4, ওটা কি 4 কিউব ইন্টু 1?
4 cube in by 3 EI,
মানে মানে F22 তে যেটা পেয়েছি ওটাই ডেল্টা বি এর ভ্যালু, তাই তো? F22 তে যেটা পেয়েছি।
obviously দেখুন আমি আপনাকে লিখে হচ্ছে
হ্যাঁ
2
ঠিক
2.
আছে, ওকে ওকে।
Okay, so now come to step 4. Step 4 is we will now frame this in the matrix and we'll find out the inverse. আগে আমরা ইনভার্সটা বার করে নিচ্ছি। So therefore now step 4. So step 4 is we will develop the matrix. So develop the flexibility matrix and find the inverse of the matrix. ঠিক আছে, inverse লাস্টেও করতে পারো, you can do the inverse at the end, but beforehand we are doing this inverse so that since we all know that this will be required at the last. Okay, so therefore the flexibility matrix, sometimes people write small f, sometimes we write capital F. Okay, no problem. Okay, so let us put the flexibility coefficient F11, F21, F12, F22. Okay, so now simply we will put these values into this. What we have got? So F11 we have got, so 1 by EI is common. If you take, so I am taking out the 1 by EI common because 1 by EI is in every coordinate. If you check, so F11 was 343 by 3 EI. Here you can turn it into decimal point, no problem. Usually I keep it in fractional form, no problem. So F11 343 by 3, F21 136 by 3. Similarly, F12 is same, and F22 is 64 by 3. Since 1 by 3 is common, you can take 1 by 3 outside also, no problem. Okay, so this is the flexibility matrix we have formed. F11, F21, F21 and F12 is same. If you see, as I told you, due to Maxwell's reciprocal theorem, and F22 we have found out. So now we will find out the inverse. All of you know how to find out inverse. Inverse will be adjunct of the matrix divided by mod matrix, that is the determinant of matrix, adjunct of F matrix by the determinate value. Okay. So what will be adjunct? See here, it will be just upside down. So EI will be at the numerator. Adjunct will be just the diagonals will be reversed. The main diagonals will be reversed, while the other diagonals will be minus. By F, so mod of F could be done to the value of so the determinate value of F. The determinate value of F you can find out. That is 343 by 3 into 64 by 3 minus 136 by 3 whole square. Find out the determinate value. Okay, we will get the value of determinate from here, and finally the value of this F inverse is coming around like this here. So F inverse, therefore F inverse, the inverse of flexibility matrix is coming around like this. 0.055 EI 0.055 minus 0.118 minus 0.118 and 0.297. So obviously before doing this you have to do this, then the value of the determinant of the matrix, and we put this. So here this will be the value of determinant, this one here. We will divide all of these values with this value, and you will get this value. So I have developed the matrix. If you want to find out the mod, that is the determinate value of matrix, you can find out. Have you someone calculated what is the value of this?
Sir,
383.99.
3456.
How much?
3456.
3456. So now, so 64 by 3 divided by 3456, just find out. 64 by 3 divided by 3456. So just check it. 64 by 3 divided by 3456, this value will come. Similarly, minus 136 by 3 divided by 3456, this value will come. Okay. So the right diagonal, if we check, the values will be same. Okay. So this is the thing. So please take it down. Next we'll go for step 5. So step 5 we'll find out the deflection due to external loading using conjugate beam method. Now the most important part, that is we have to apply conjugate beam method or moment area method. Okay. So it depends on you how you are suitable with the methods. Okay. If someone is suitable with moment area, then you can apply moment area method. If someone is suitable in conjugate beam method, he or she can apply conjugate beam method, no problem. Okay. So step 5. Step 5 is the deflection due to external loading. Step 5. Determine delta 1L and delta 2L. That is the displacements due to external loading. Displacements due to external loads. This will be external loads. Okay. So delta 1L and delta 2L. Now we will put on the primary structure, we will put the external loads. Newton, and here we had the UDL. So now at this point, so this is coordinate 2, this coordinate 1. Okay. So now at this point, let us take this point as. So at this point now we will apply. So we will find out what delta 1L, that is deflection at coordinate 1 due to external loading, and delta 2L, deflection or displacement at coordinate 2 due to all the external loading. So now we will apply. Here I am applying conjugate beam method. If you feel moment area is easy, you can find out, no problem. So all of you know in moment area and conjugate beam method, we find out the value, the diagram M by EI diagram. All of you remember M by EI diagram. It is a moment divided by flexural rigidity diagram, M by EI diagram. To apply conjugate beam. Here I am applying conjugate beam. You can make apply moment area also. Moment area, as you wish, no problem. Okay. So we will draw the diagram. M by I diagram, obviously it will be straight till this point. It is linear, as you know. It will be like this curve. Because it is UDL, so the bending moment diagram will be parabolic. Okay. So this is M by I diagram. So the total diagram is a combination of triangular, linear, as well as parabolic. Okay, so now we will find out first delta 1L. That is the total deflection at C. Not total deflection. Delta 1L is the deflection or the displacement at coordinate 1 due to external loading. That is delta C. Okay. So here we will apply. So the bending moment here it is obviously negative. So delta C. Now we will apply the conjugate beam method. What is the formula? We know that. So E1 x1 bar plus A2 x2 bar, all these things. Okay. So rather directly we will go A bar x bar. Total area within this and the CG distance. So minus. So bending moment diagram is minus. So point load. So W into first C. So A, B, I have put another point D. Okay. So 100 into AD cube. AD cube by 3EI. Okay. Obviously, I will not show the support. I mean, obviously, we will not show the supports here because it is a primary structure. Okay. So just imagine. So you add D is there. How much it is? BD cube by 3EI. Correct. Then what will happen? Then we will have the slope, that is PL square by 2EI. PL square by 2EI into CD. Is length by CD. Plus due to UDL 60 W into L to the power 4 by 8 EI. You know the deflection due to UDL PL W L to the power 4 by 8 EI. Okay. So see this one plus obviously the PL square. This one by 6 EI into BC. So see here what I am done. Simple. First is I am doing for what? This 100 kilonewton. Okay. So for 100 kilonewton, what is the effect at 1? We are not finding the effect at 2. We are only interested to find out the effect at 1. Okay. So 100. So see minus is due to all the coordinate is minus. So minus I have taken outside. First PL cube by 3EI because point load. So P is 100. PL cube A will give how much? ADPP length. So PL cube by 3EI plus theta D. Slope at D is how much? PL square by 2EI. 100 into 80 square by 2E. Sorry, I into length CD. Why length CD? Because I am finding this effect at 1. Next, similarly for 60 kilonewton per meter UDL. For UDL, what is the formula? WL to the 4 by 8 EI. Deflection due to UDL on cantilever. You can just go and check. So 60 into AB to the 4 by 8 EI plus this one. So deflection at B, that is 60 into AB cube by 6 EI plus BL BC. That is the slope here. Slope at B into BC. Okay. So find out the values. Slowly tell me the values. So the whole thing is coming. If you take the minus outside, 100 into AD was AD is 4.5 cube by 3 EI. You can take EI outside also if you feel. 1 by EI common. So first is 100 AD cube by 3 plus 100 AD square by 2 into CD. CD is 1.5 plus 60 into AB. BC. This is so calculate and tell me the answer. Slowly calculate and tell me the answer. What is the total value of this? All of you are you calculating? Calculate and tell me the answer slowly. How much is the answer? How much it is coming? Tell me the answer. Everyone is sleeping during the calculation time.
8396.25.
Oh, এক মিনিট আমি একটু ভুল করি sorry just a minute I did a mistake here. AD is how much? AB is 4 meter, BD is 1.5, so AD will be 5.5. 5.5, change the 4.5 to 5.5, sorry. So 100 into 5.5 cube by 3 plus 100 into 5.5 square by 2 into 1.5. Yes, now you calculate slowly. Slowly calculate, there is no hurry. How much is the answer? This will come around minus 11654 11,654.58 by EN. Have you got this answer? This is the answer. Okay. Similarly, delta 2L, that will be delta B. Have you got this answer, anyone?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
আচ্ছা,
Yes, sir.
now এবার delta B এর জন্য বলো তোমরা কত হবে? You tell me. I will not tell the formula. For delta B, that is the deflection at coordinate 2 due to the so B for B. Okay, so you tell me what will be the value. Okay, what will be value? You tell me. Yeah, first we have 100 kilonewton, so we have to see even though B is there, B is before D. But even the B before the you take this consideration of 100 kilonewton, so it will be PL cube by 3EI. So P 100, L will be AB because BD is not present here. So 100 AB cube by 3EI, right? Plus that is my slope, that is PL square, P 100 into AB square by 2EI, that is slope, into BD, okay, right? Oh, sorry, I did a mistake here. 100 into AD cube, sorry, 100 into AD cube, 100 into AD cube by 3EI plus 100 into AD square by 2EI AD into BD plus UDL WL to the power 4 by 8EI. This much. So it is coming around minus 5253.33 divided by EI. So therefore, now I will put in the compatible equation, that is R equals to F inverse into minus delta L F inverse into minus of delta L. This is the compatible equation, okay? R, okay? So R is unknown, okay? So R, or sometimes we may write P, no problem. P is equals to F inverse into minus of delta L, same thing, okay? So therefore R is the unknown. So R is two unknowns, R1, R2. R1, R2 will be equals to F inverse, the value which we have got. So I am framing the matrix, you tell me the value of R1, R2, okay? So the inverse matrix, I am writing the values. That is EI 0.055 minus 0.118 minus 0.118 and 0.297. So this was the inverse, correct? Into, so delta L, put the values of delta L, that is minus of minus 11654.58 minus of minus 5253.33. So you will find, tell me the answer of R1, that will be RC, and the value of R2, that will be R. You will tell me. Slowly solve it and tell me. 1 by I gets cancelled. You will tell me the value. Slowly calculate. So you have this matrix and minus minus plus. So all these will get plus. So plus 11654.58 and plus 5253.3. So multiply, do matrix multiplication and tell me the answer. You will tell me the answer of RC, RB and also RA. RC, RB as well as RA. How much? The answer R1, R2. তাড়াতাড়ি বলো. I think you should know the matrix multiplication.
Sir,
Please don't tell
R1
me to
is
speak.
Sir, R1 is
Yes.
21.1089 kilonewton.
Who is this? Who told me the answer?
1089 kilonewton.
Nidhi, Niharika. Okay, very good. Shabash. Next, R2.
Sir, 185.
185 kilometer. Correct. So R1 is 21.10 coming. I'm rounding it off. And R2 is 185 kilometer. RA निकाल सकते हो? RA थर्ड सपोर्ट का जो रिएक्शन है RA वो अननोन है. निकालो. कैसे निकालोगे? RB RC तो मिल गया. अब RA बाकी है. फाइंड आउट. I hope you know how to find out RA.
Sir, 133.9 kilonewton.
Excellent. RA is 133.9. बहुत बढ़िया. ठीक है. तो दिस इज हाउ. देखो ये एक बहुत मस्त चीज है. बहुत बच्चे लोग ये क्या करते हैं. the main problem is that many students face this problem. सर यहाँ पे 3 तो अननोन है. ठीक है. In many exams, in many MCQs, or in many questions, it comes that find out the shear force diagram. Okay, or draw the shear force diagram. So you can find out RA, RB, RC. You can draw it. Sometimes it tells us this find out the unknown reactions. RA, reaction at RA. Okay. What we had learned initially, we had learned in structure analysis 1. We had learned moment area. We had learned conjugate beam. All these things. Okay. Another method आज हम लोग सीखे हैं. Using flexibility matrix method also you can find out the unknown reaction. Length थोड़ा, the method is lengthy, but see we can easily find out the reaction at A and B and C without any problem. So if we use the force as redundant, यहाँ पे देखो यहाँ पे difficult नहीं है ज्यादा. Formulas भी simple है. सिंपल एक ही फॉर्मूला हम लोग यूज कर रहे हैं. दैट इज मान लो कोई भी पॉइंट में जस्ट कंसीडर एट सम सर्टेन पॉइंट द लोड इज देयर. यूटीएल और पॉइंट द लोड इज देयर. सो एट दैट पॉइंट वी कैन फाइंड आउट द डिफ्लेक्शन using the slope deflection formula. Or if there is some different point, then what we'll do, we are getting the deflection, that is slope, then deflection, original deflection into slope into length. This simple thing. Using this matrix method, we can find out unknown reactions A, B, and C, which we had earlier used methods like consistent deformation method, moment area, conjugate beam method, all these things. Okay. Method 2 जो है, if you follow method 2, let us do method 2. Okay. So method 2 will be completely similar. Acha, the method 2 by which I will teach you is slightly different from Bhavikatti. If you see the book of SS Bhavikatti, the method 2 is given. Okay, they have taken the moments unknown. Obviously, that is an important method. If bending moment is required, अगर shear force चाहिए तो यही method यूज करना. अगर bending moment चाहिए तब ये method हम लोग we can find out, no problem. Okay, but the alternative method is also there. Okay. And if you use bending method, bending moment, it is slightly smaller. If you use the second method, that is taking the bending moment as unknown, the method is slightly smaller compared to method 1. Okay. So let us come to method 2, the alternative method. Alternative method is given in Bhavikatti, that you can follow, or you can follow the method which I am teaching. Both will give you the same result. Okay. So do not think that my method and Bhavikatti method, they are different. Method 1 was different, absolutely. Method 1 there nahi hai. Method 2 is completely almost similar. The answer will come same. Okay. But this method, my method, is slightly easier. So come to alternative method. Where moments at supports are taken as redundant. Moments at support is taken as redundant. ओके तो यहाँ पे प्रॉब्लम क्या है बोले डिसएडवांटेज इज यहाँ से हम लोग shear force diagram नहीं कर पाए ओके here we cannot find the reactions only the end moments we can do so we can draw the bending moment diagram but shear force diagram करने के लिए we have to apply method okay so SFD and reactions at support is not available cannot be accessed ठीक है SFD and reaction support cannot be accessed but from method 1 से हम लोग कर सकते हैं है ना from method 1 we have got RA RB RC so we can do a bending moment diagram shear force diagram अगर कर पाएंगे तो bending moment diagram भी कर पाएंगे ठीक है see here so moments so here यहाँ पे क्या है first step 1 is we all know that is ds is 2 here क्या हो रहा है we will convert the structure into static and determinate structure देखो I have turned all the supports into simply supported. See it very carefully. In this method, alternative method, method 2, we will convert the total beam into simply supported beam. Simply supported beam. And we will take moment A at unknown. Moment A, coordinate 1, moment B as coordinate 2. Why? So see first let us so we'll convert the prop cantilever beam into simply supported beam. Convert prop cantilever that is indeterminate into simply supported beam. Okay. Now why we are taking this coordinate 1 and 2? Why not C? Because अगर C में देखोगे, if you take C, we all know that C is the far end, that is the end point, and it is hinged point or simply supported at C. Moment at C will be always 0. So moment at C will always be 0. Why? Moment at fixed end is unknown. Moment at intermediate support is unknown. That is why I have taken moment A and moment B as unknown. आया समझ में क्यों हम लोग लिए हैं वेरी इंपॉर्टेंट फाइंड आउट डीएस तो निकाल लिया अब आइडेंटिफाई करना है मेथड 1 के लिए हम लोग क्या आइडेंटिफाई किए थे इन मेथड 1 we found out RB and RC as unknown in method 2 we have taken MA and MB not MB and MC because C is at the far end okay so whenever you will see that far end में single supported है either hinged or roller support directly moment 0 तो अननोन एक निकल गया तो दो ठो अननोन रह गया MA that is at fixed end we know the moment is not non-zero it is not zero actually it is non-zero and intermediate support में the moment रहेगा okay so now so AB and BC okay so now we will divide AB and BC so here we will apply A and B ठीक है so A and B single supported beam so now we will find out the flexibility matrix correct this is case 1 केस 1 में क्या हो रहा है, मोमेंट ए एज 1 किलोमीटर मीटर, यहाँ पे भी द फोर्स एज यूनिटी, यहाँ पे फोर्स क्या है, मोमेंट एज यूनिटी. आई टोल्ड यू लास्ट डे, generalized force meaning force as well as moment. So moment here is unit. So flexibility matrix, so put MA as 1 in first case. then क्या होगा, F11 F21. So what will be F11? If we have one end as a simply supported beam and one end is subject to moment, correct? So moment के लिए what will happen, we have slope theta है, okay? So FA will be what? FA will be slope. If you see the chart, at sent you, it will be 4 by 3 here. Do make print out the chart 4 by 3 here because it is L by ML by 3 here. Simple. ML by 3. Length is 4 meter. M is 1. So 1 into 4 by 3. You have to go to the chart. Okay. Then only you can find out. Okay. So F11, similarly F21. F21 will be theta B. Correct? So 4 by 6 CI. So then means that it will be ML by 6 CI. Okay. Similarly, case 2 में, in case 2, similarly in case 2, that is A and B, case 2. So we will have moments at B. So MB 1 kilometer meter, theta B. So due to moment we have theta B and theta A. So case 1 में क्या था? At coordinate 1 I had put moment at 1. So this is coordinate 1, coordinate 2. Case 2 में क्या होगा? I am putting unit moment at coordinate 2. तो यहाँ पे क्या होगा, F22 वही है, so first of all F12 will be ML by 6 CI, ML by, that is 4 by 6 CI, 4 by 6 CI, and F22 will be how much, theta B AB, theta B into length AB plus theta B into BC, because there is also BC is there. BC is there. So like this we will proceed. So F11, F21, F12, F22. So B में क्या है? B is intermediate support at AB as well as BC. You have to consider the effect of AB as well as BC. So it is coming 7 by 3 here. So therefore, the flexibility matrix the flexibility matrix 1 by EI is coming 4 by 3, 4 by 6. All we know that F21 and F12 is 10, 7 by 3. Okay. And F inverse, if you check it, the F inverse is coming as this. EI divided by into 0.877, 0.501 minus 0.251 minus 0.2. In order to find out the flexibility coordinates, Bhavikatti has taken a different method. So we have got the flexibility matrix, flexibility inverse matrix. Okay. अब क्या करना है? Delta 1L, delta 2L. That is delta 1L at A and delta 2L at B. ठीक है? So वही single supported beam in the beam of AB. Now what we'll do? We will put the UDL and as well as in BC we will put the point load. So delta 1L will be slope at A, Gounod slope, that is 60 into 4 cube by 24 EI. Okay. And delta 2L, that is theta V into length AB plus theta C into length BC. And finally, we will put it in the compatible equation. Delta this one. Okay. And find out, you will finally, so therefore finally R1 will be MA and R2 will be MA. R2 will be MA. So copy this down. Okay, so now attendance. Have you copied? Will you copy this down?